Friends, today we'll be talking about fracture. First of all, we'll try to understand what is fracture. Actually, it is very commonly used. Usually bones are fractured when you meet with an accident. So actually we all know, but in engineering terms, what exactly it means is separation or fragmentation of a solid body into two or more parts under stress. Under stress is called fracture, and it has got two stages, stage 1 and stage 2, right? And this fracture can be categorized into various nomenclatures are there, but today we will be discussing fracture in terms of mode ductile or brittle. Ductile or brittle fracture, right? Actually, ductile fracture is the type of fracture. Does not necessarily mean that a ductile material can fracture in a brittle way, and a brittle material can fracture in a ductile way. So the mode of fracture are two, ductile and brittle. What is the difference? The difference is when you call a ductile fracture when the fracture there is substantial deformation prior to and during crack propagation. That means before the separation into two parts or more parts takes place, there is lot of elongation or plastic deformation taking place prior to or during the fracture process. Then it is called ductile fracture. Whereas in brittle fractures, there is negligible prior deformation to fracture, to crack propagation, fracture, right? So these are the two modes of fracture. So what we will be doing is, today we will be studying about fracture of metals, right? When I say metals, the first thing which you should know is that they are crystalline in nature, and metals are crystalline. Metal fracture. Why I am taking metals is that it is one of the most popular engineering materials, especially mechanical engineers are dealing with metals and alloys. So metals, they will also fracture either in ductile mode or they will fracture in brittle mode, depending upon, there are three things, that is strain rate, temperature and state of stress. Depending upon the strain rate, if the strain rate is very high, usually metals are ductile, but they can give you a brittle fracture. You understand what I meant? They are ductile and brittle, they are simply modes of fracture, right? Apparently metals which are ductile can give you a brittle failure if very high strain rate is there, or a a very low temperature is there. The classic example is the Titanic. All most of you have, I think, seen the film Titanic. Actually, when the glaciers are there are sub-zero temperatures, and at that temperature, the ductile materials, they behave in a brittle fashion. That will require another lecture. What is ductile to brittle transition, at what temperature the transition takes place and all. And then the state of stress. Usually when there is a triaxial state of stress, the deformation is difficult and the yielding is difficult, and you usually tend to have a brittle fracture. So first thing which I wanted to tell you was that not necessarily a ductile material may fail in a ductile fashion, or it may give a brittle fracture as well as a ductile fracture. So let us first take two cases, two kinds of stressing. Number one, uniaxial tension. Suppose a metallic specimen has been subjected to uniaxial specimen. Let us take a very simple form, a cylindrical material, say and it has been subjected to uniaxial tension, right? Say sigma and sigma. First thing what we will be doing is we will finding out what is the stress state. We will take out an element from here. So this is one element and it is under tension, sigma, sigma, xy direction. So let us draw the Morse circle of this, right? This is sigma and this is tau. So sigma x is 0, sigma y is sigma, right? And there is no shear stress here. So the Morse circle becomes this. So the maximum shear stress in this case is tau max, which is equal to sigma by 2, and the first principal stress sigma 1 is equal to sigma, and the minimum principal stress is 0, right? So what I have found out is that when you apply tensile stress, you have the maximum principal stress as sigma, minimum as 0, and maximum shear stress as sigma by 2. So in my ductile material, usually the ductile materials, there are two kinds of materials, right? First I will take single crystal, right? And single crystal, and there is another which is polycrystal, right? If you take single crystal or polycrystals, first I will take brittle fracture. How brittle fracture takes place? If the nature of fracture is brittle and it is a single crystal or polycrystal, suppose this is my crystal, when it fractures, it is a flat fracture like this into two parts, right? If it is a single crystal, there will be a facet available which will shine, and if it is a polycrystal, then to gross direction of the crack will be 90 degree to the tensile axis. Why? A brittle material is strong in shear, right, or sliding, and weak in normal stress or separation. What I mean here is that it has very low resistance to separation, but it has very high resistance to sliding. So that's the reason why it fails the normal stresses, maximum normal stresses, the principal stress sigma, and when it is applied in that direction, so perpendicular to the direction, the fracture takes place. Both single crystals as well as polycrystals, they give me a brittle fracture of this nature, flat. This is called flat. But when you come to a ductile fracture, we'll have one single crystal case, and another one that is polycrystal clay. Polycrystal. Look, single crystals are very rare, but I am taking them because suppose there is a single crystal, it will have a definite slip plane. These materials, they are weak in shear. The ductile fracture takes place when the material is weak in shear or sliding and strong in normal stress. Or separation. That means it has got high resistance to separation. So it won't break into two pieces in this way. It will slide, and the maximum shear stress is at this position, which is 90 degree on Moore's circle, means 45 degree to the tensile axis. This is 45 degree. So the maximum shear stress is at 45 degrees. So whatever slip plane is nearly available at this angle or some angle to it, that will first fail, right? So because they are weak in shear, so the failure is via shear. So basically the sliding takes place like this. Then strain hardening takes place, the slip goes to the other direction, and I am not going to go into the deep. Basically this slip system makes it rotate like this. So ultimately the fracture is into two parts when they break like this, right? This is what happens in a single crystal. But when you take the case of a polycrystal, it has so much things going inside it. I'll take a case which is ideal, but very rarely you have that kind of a case. If you have a very pure material, pure metal, or very high temperatures. When temperatures are very high, you will find that slip, this is 45, this is 45, it will go like this and go on elongating, necking will take place to the extent that it will become a point, and then it will fracture. So you will find that a polycrystalline metallic sample will fail like this. But this never happens, friends. This will only happen when the metal is very, very pure, vacuum, it is vacuum melted, there is no second phase particle, and it is only and only the crystal and no inclusions, nothing. or the temperatures are very high, so metal flows, actually shear takes place, and which is maximum at 45 degrees, so that's why it necks like this and ultimately elongates, and when it remains, a point remains, it breaks. So this is how it happens. Now we'll come to practically real case of a polycrystalline material, what happens and how it happens. It's a very typical case. Ductile failure of a polycrystalline material. It's a very, very important thing in engineering, right? What happens? Suppose first of all I'll draw the stress strain diagram. Stress and strain. We all know the stress strain diagram for a ductile material is something like this, right? This is the yield point. This is ultimate tensile strength. It is actually the point of instability, point of instability, right? And at this it fractures. This is engineering stress strain diagram. Actually, when the true stress strain diagram you take, it looks something like this, right? Because at the point of we'll start from here. As it is a ductile material, there is a prior deformation going on, right? So let us start from, this is the elastic portion of the deformation. That means the sample, suppose it's a cylindrical simple sample, there will be reduction in diameter like this. But when you reduce the stress, it will come back to its original diameter, length, everything will be recoverable. But as soon as it passes the yield point, you will have permanent deformation, right? And that is plastic deformation. The size will reduce, the diameter will reduce, right? But when you reach this point, it will not only be simple reduction in the diameter, you will see this is point of instability. I'll explain later what is instability. You will find that this kind of necking starts. This is called necking. And this necking goes on, and at this point it fractures. This is true stress strain diagram. True stress strain diagram. Now what exactly is happening inside? Let us see, right? The fracture which takes place has a nature of cup and cone. This is called cup and cone fracture. Why this happens? So we'll study what exactly is happening after this instability. We all know what is happening. Deformation mechanism is a different chapter altogether. We are interested in fracture. So let us start from here to here. What is happening? Actually, when there are second phase particle, although the material is ductile, what happens? At the point of instability, a small neck starts. Why it starts? I'll tell you. It's a localized thing, right? It's a very localized phenomenon, and this neck will go on increasing. This neck will go on increasing. Once it starts, it will go on this cross section. It will not happen here. It will not happen here. The question is why it happens somewhere. So that's the reason why it is called instability. Just like you are on the top of a hill, you can fall this way or you can fall that way. That's the reason why it is called instability, point of instability. What happens actually in real materials which are not pure, you always have second phase particles which are brittle, intermetallics, right, or inclusions. So inclusions, or if I enlarge this portion, what it will look like is these are inclusions or second phase particles. These are intermetallics. They are not metallic bonds, and hence these are all brittle in nature. Brittle. So even if one of these fractures, the moment it fractures, what happens? There is nothing here. I'll again enlarge this. That means there is a gap here, right? In this portion, this is air, nothing. So if there is no material here, that means the area, effective area, has reduced. Similarly, another way this can happen is either this can happen, or another thing is, if this is the material and this is the metal, there may be some debonding at the interface, or this is fracture of particle. When the fracture of particle takes place, or there is debonding, there is a gap here. Soon as this happens, the stress at this particular area increases. When it increases, further any other such particle, it will be more here compared to other areas. So that's the reason why any particular location, you don't know where this necking will take place. Once it starts, the moment it starts, it will go on increasing at this particular location. This may be here, this may be here, we don't know, but it will start, right? So this kind of phenomenon occurs, and what happens here is, although we are applying tensile stress and the material is going to shear, what has happened here is there are some micro voids. Due to fracture or debonding of particles, right? So once this has formed, what happens? Actually, the stress distribution here, the moment there is a radius, I'll show you what happens when there is a radius of curvature. Whenever there is a radius of curvature, the stress distribution becomes this. The stress distribution is not simple. If you go away from this part, the stress distribution is uniform. This is sigma stress. But here, the stress distribution becomes this. If you take the central axis, the stress here is sigma max, and here it is sigma minimum. So the stress distribution is like this. It is maximum in the central portion and it reduces, right? In fact, it is inversely proportional. If you see sigma max upon sigma min, it is 1 plus a by 2r, if r is the radius of curvature of the neck. So you see that maximum stress is at the center. Because of the formation of this neck, the maximum stress is at the center. So what happens? Actually, we are trying to understand how this cup and cone fracture occurs. As soon as the neck is formed, the stress increases here. Because the stress increases, you will find in the central region there will be some micro voids, and then these micro voids will coalesce. It is called micro void coalescence, and a crack will be formed. Micro crack, you can say, micro crack formed due to micro void coalescence. Due to micro void coalescence. And once this has been formed, the next stage is, that means if you stop the tension test and you cut and polish, you will find a crack in the center. If you go on loading, this crack is going to increase. The direction of the crack is perpendicular to the tensile axis, right? But this portion, the rest of the portion, it shears like this. These are shear regions, and this is having perpendicular, this is due to shear, and this is at almost 45 degree, right? So these are called shear lips, and that's the reason why this results into cup and cone fracture. So friends, you have seen, although we are elongating a ductile metallic specimen, you don't have a simple kind of fracture. There is a brittle fracture involved in the center, and only the ductile portion is at the edge where the stresses are not very high, and the shearing takes place, and you find a cup and cone fracture. So this was all about the ductile fracture in case of simple tension. Now let us take the case of torsion, right? Case number 1 was tension, tensile loading, now torsional loading. We all know what is torsion and torsional loading, what it means. Suppose this is my round bar and it is subjected to a twist, right? T torque. We all know from strength of material that there will be a shear stress which will equal to TR over J, right? So we'll again take out an element from here to check what is the stress state here, right? Let me pluck this element out. The very first step is always the stress analysis, because let us understand first what's happening, what kind of stresses are being applied. Then after we'll see what kind of behavior it will show. So this is how it happens, right? Tau tau. Let us draw the Morse circle. There is no sigma x, 0, sigma y, 0, tau xy is tau. So the Morse circle becomes maximum principal stress will be tau and minimum principal stress will be minus tau, right? So this is what is happening. If I check with a first ductile fracture, ductile fracture under torsional load, what happens and how it happens? We all know ductile fracture occurs when the status is that it is weak in shear or sliding and strong, there is strong resistance to separation, right? So if it is weak in shear, maximum shear stress will lead to failure, right? And you see maximum shear stress is here itself, so it is as simple as that. The failure takes place like this, right? But when you take brittle fracture, we all know brittle fracture will occur when it is weak in separation and strong in shear or sliding. So we'll have to check where we will find, because it is strong in shear, it is weak in separation. So we'll have to find, we are not now interested in shear stress, we are interested in normal. Separation means normal stress, normal tensile stress. So in this case we know that it is at 45 degree, and if you rotate this element by 45 degree, what you will have is this, you will get these values at 45 degree and it will be like this. So a simple pure torsion is, you can say, a stress state in which there is a combination of tensile and compressive stresses, which is equal to tau, tau, tau and tau. This is minus, this is minus, this is plus and this is plus. This is tensile, this is compressive. These are the two maximum minimum principal stresses. Compression will definitely not lead to crack formation or propagation. Crack formation and propagation will be not there. It will be there when there will be tensile kind of a load. So if you see here that, because this is tensile, this is tensile, so this will lead to crack formation and propagation, right? This will lead to crack formation and crack propagation. So you will find that at 45 degree the crack will take place, and hence the helicoidal fracture takes place. You will find that there will be a helicoidal kind of fracture. like this, right? This is helicoidal fracture. So we'll sum up. In tensile test, the brittle fracture was like this separation, right, in two parts. Ductile fracture, single crystal, there was a shear failure at some angle like this, right? And when it was a polycrystalline material, it was a classic cup and cone fracture. There was necking and then cup and cone fracture. Coming to torsional load, if you have a ductile fracture, if you go on twisting the material, you will find that it has failed like this. It has failed like this. If you take the case of mild steel or copper, you will find that it has failed in a flat fashion. This is flat. This is flat fracture, right? But if you take the case of brittle fracture, it will have a helicoidal nature, and I'll give you an example. We all know that this chalk, the chalk is a brittle material, right? I will apply a torque load and let us see how it fails. This is how it fails. You saw a classic fracture which is helicoidal in nature, right? You can see here. This is how I told you the brittle material fails in torsion. So brittle material fails in torsion in a helicoidal fashion. When it is a ductile material, when I twist, it will fail like this. When you have a tensile specimen, the brittle material, it will fail like this, flat fracture, and a ductile polycrystalline material will give a cup and cone fracture, which is a classic fracture. So I hope all of you have understood the macro mechanism of fracture, and I wish you that in coming lectures we'll go in further depth and study the micro mechanism of fracture. Thank you all.